Hello, my name is Marvin Petit-Home, Global Residual Products Manager for IPCO. We are delighted to be here today to discuss our core technology and our solutions for the industry. Before I dive into our core technology, I would like to take a minute to introduce IPCO. Who are we? IPCO began its journey as Sandvik Process Systems. IPCO was part of the Sandvik Group for well over 125 years. In 2017, IPCO was divested to the Wallenberg Group. The Wallenberg Group is an industrial Swedish holding company with over 600,000 employees and over 140 billion euro in annual turnover of its sales holdings. Today, IPCO is present in 35 countries to serve our customers. To be clear, IPCO is not a licensor of residue upgrading technologies. However, IPCO works with some of the leading technology licensors, such as Axon, CLG, KBR, UOP, and Wood, to incorporate IPCO's core technology into their process licenses. Over the last 5 years, IPCO has seen an increased demand for its core technology and solutions from these licensors. The core technology and the demand for our core technology is really being driven by a resurgence in the demand for residue upgrading technologies, which is in turn being driven by global clean fuel legislation, and also a need for refiners to integrate their assets or their unit operations with the petrochemical market. IPCO's core technology enables the licensors to actually manage the asphalting or pit stream from the various bottom of the barrel processes. IPCO offers solidification systems to convert liquid pitch into a solid form. The solid form can be used for combustion, gasification, and other industrial applications. IPCO typically receives the liquid pit stream from a Solvent Deasphalting unit or SDA unit. The pit stream is sent within IPCO's battery limit. IPCO offers two core technologies to be able to transfer the liquid pit stream into a solid form. The first technology that we will be discussing today is IPCO's flaking technology, which is based on our double belt cooling technology. The second core technology that we will be discussing is based on IPCO's rotiform technology to produce more random, more uniform sized pellets. Whether it's a flake or a pellet, the product is could eventually be sent to a CFB or a gasified. IPCO's flaking technology. As I previously mentioned, IPCO's flaking technology is based on our double belt cooling systems. What is a double belt cooling system? A double belt cooling system is essentially a lower steel belt conveyor with a upper steel belt conveyor mounted over it. The essential product is actually sandwiched between two thin stainless steel belts, conveyed through the cooling section, and discharges as a free-flowing product. A little bit more detail regarding the double belt cooler. Typically, IPCO, we will receive the liquid pitch stream, the molten form from a pitch surge drum through jacketed piping via a positive displacement gear pump. The system includes a specifically designed feed manifold that takes the liquid pitch stream and distributes a thin layer, approximately 3 to 4 millimeters thick, across the width of the lower steel belt. The lower steel belt is typically 1.5 meters to 2 meters wide, depending on capacity needs. The liquid pitch layer is transferred from the lower belt and gets fed into the upper belt section. As a liquid molten product, which is typically somewhere about 250 to 300 degrees Celsius, is conveyed into the upper belt section. The heat from the actual product is transferred from the liquid pitch to the upper steel belt and to the lower steel belt. cooling water is sprayed on the underside of the lower belt and also on the inside strand of the upper belt. Thus, the heat transfer from the product is in two directions. The heat is transferred from the product to either of the steel belts, and then from the steel belts to the actual cooling water. The cooling water temperature is typically between 30 to 40 degrees Celsius. The heat pickup from the product is usually in the range of 5 to 10 degrees Celsius. The warm water from the process from both the upper and lower belt drains by gravity into a water collecting tank or a pit. This warm water is pumped through a centrifugal pump to a heat exchanger, typically a plate and frame heat exchanger, to expel the heat such that the cooling water is pumped back into the process in a closed loop fashion. As the liquid pitch travels down the length of the conveyor, it solidifies into a sheet. Upon discharge on the lower belt, the sheet is introduced into a product breaker. The product breaker breaks the solidified sheet into random sized particles that are roughly 50 millimeters by 50 millimeters. And from the product breaker, the material is typically conveyed into the material handling system for the plant. Depending on the type of pitch, vapors will form at the feed end area. To handle the vapors, typically we will actually exhaust the vapors into a carbon canister, again, depending on the composition of the vapor stream. We can handle the vapor and pass it through a carbon filter or carbon bed to remove odor, and then the exhaust can be sent to the atmosphere. Alternatively, the exhaust could be captured and sent to the plant flare system. To the left is a 3D model of what the double belt cooler looks like. The unit is typically, as I mentioned, 1.5 meters wide to some 4 to 2 meters wide, and approximately with 40 meters of cooling. The product that is produced is typically 50 by 50 or 25 by 25 millimeters with 3 to 4 millimeter thick sheet. The bulk density averages between 600 to 700 kilograms per cubic meter, and the heating value is typically 37,000 kilojoules per kilogram. The capacity of the double belt cooling system, it could range depending on feed conditions to anywhere between 250 and 400 metric tons per day. In comparison, the second system that IPCO offers is our pastillation system. The pastillation system is based on IPCO's patented rotiform technology. The rotiform technology, which we'll describe in a few minutes, is basically a rotary depositor that deposits individual molten pastilles on a lower steel belt. Typically, as with the flaking process, we receive the pitch from the SDA unit, and it's stored in a surge vessel. And just like the flaking process, the liquid pitch is pumped through jacketed piping via a positive displacement gear pump. And in this case, in order to protect the openings of the rotiformer, we typically employ a jacketed duplex filter to filter large particles prior to introducing them into the rotiform head. As I mentioned earlier, the rotiform is a rotary depositor that takes the molten pitch and distributes it across the width of the belt. It deposits individual molten pastilles or pellets onto a moving stainless steel belt. As with the flaking process, the belt is typically 1 millimeters thick, approximately 1.5 meters wide. And as the pastilles, like the flaking process, travels down the length of the belt, cooling water is sprayed on the underside such that the heat from the product is transferred from the product to the steel belt, from the steel belt to the cooling water. And again, just like the flaking process, the heat picked up from the rotiform process, from the steel belt, from the water, is typically, in this case, in a range of 5 to 8 Celsius. And this warm water is collected into a tank or a pit and then sent to the plant water system or a heat exchanger to expel the heat, and then the cooling water returns in a closed loop fashion. As the individual pellets travel down the length of the belt, they discharge into a free flowing particle. Unlike the flake process where we employed a product breaker, with this waterform process, the pastilles are actually formed and they are uniform, and there's no need to go into any other size reduction, and the material can be conveyed into a takeaway conveyor to the plant material handling system. Similar to the flaking process, the exhaust closer to the feed end will be exhausted, and it could either go to the plant flare system or to a activated carbon bed to remove odor, and then to atmosphere. And one distinct factor, which we will talk about later, is the heat transfer rate as compared to the flaking process with the rotiform process. One of the interesting things that IPCO does is we actually work with our clients from the beginning of a process. We will definitely look at evaluating the pitch in a dynamic setting, or also in a pilot setting, to really understand what the pitch physical properties are. Thus, as we're comparing pastillation and flaking, we go through this evaluation process so we can help our clients select the best technology for their pitch. And also, we also consider what the end product will be used for, whether it will be used inside the refinery gates for a CFB application, or whether the client is looking to actually take the pitch and sell it in the marketplace. So all of these factors will help IPCO help the client select which is the better form to actually produce. Thus, in comparison of the pastillation versus flaking technology, the pitch feed temperature is typically for pastillation 300 degrees Celsius max versus 350 max for the flaking process. And the difference between the max feed temperatures is based on what I described earlier, is that the pastillation process is based on a rotiform process, which is a rotating piece of equipment. And finding greases, seals above 300 degrees Celsius becomes a challenge for this process. Thus, we limit the maximum temperature to about 300 degrees Celsius. The pitch viscosity is also an important physical property to help us understand. 3,000 millipascal seconds for pastillation and about 10,000 millipascal seconds for the flaking process. One key physical property is the pitch softening point. Regardless of if it's pastillation or flaking, we will limit the minimum softening point to about 100 to 120 degrees Celsius for either process. The pitch softening point is an important characteristic because it definitely helps us determine what the pitch discharge temperature is. The lower the softening point, the lower temperature that we have to discharge either pastilles or flake from our process. And the minimum softening point of about 100 degrees Celsius, also, we have to consider what would occur in the downstream handling equipment. Lower softening point pitches will tend to agglomerate and definitely solidify in the actual downstream component. So managing the discharge temperature in relationship to the pitch softening point is extremely critical. The cooling water temperature that we typically use is between 35 and 45 degrees Celsius. Obviously, the biggest difference that you can see between the two processes is that the maximum capacity we can obtain on a single train with the pastillation or the rotiform process is 100 metric tons per day versus 400 metric tons per day for the flaking process. And this is an important characteristic as it has a significant impact on OPEX and CAPEX. As I stated earlier, one of the big differences is the heat transfer rate when we compare the flaking process versus the pastillation process. If you could remember, in the flaking process, we were utilizing two belts, one a lower belt and an upper belt. The product was sandwiched between the two belts. Thus, the heat transfer rate is in both directions, from the top and then from the bottom. So thus, we're able to actually extract heat faster from the actual layer of pitch into the cooling water. As compared to the pastillation process, the heat transfer rate was in one direction with the lower belt. In addition to the faster heat transfer rate, the flaking process, as we were laying a sheet on the entire width of the lower belt, we're utilizing more of the surface area of the belt for production versus the pastillation process. In the pastillation process, in order to provide and make uniform pastilles, basically we're utilize, say, 75% of the available surface area of the belt to be able to supply small uniform particles. Thus, 25% of the belt surface is left open. So those two reasons help understand why there's a big difference between the capacity of the pastillator versus the flaker. To help drive that point home, if we take a look at a process plant of a typical 500 metric tons per day plant for pitch, based on the pastillation case, we will require 5 machines at 100 metric tons per day each for the pastillation. This will require a plot area that's 25 meters by 50 meters, and with 5 units. If we take this look at the same process plant with the flaking process, we will utilize two trains. Each train is typically 1.5 meters by 40 meters long. The plot area will be 12 meters by 15 meters. Thus, you can easily see that there is a extreme advantage when it comes to CapEx and OpEx advantage for flaking versus pastillation. So the logical question would be, when would someone consider a pastillation process? As I mentioned earlier, one of the advantages of the pastillation process is that you are producing a uniform particle. That uniform particle definitely is less friable than the random size flake particle. Thus, the pastillation process, it has better mechanical advantages, and especially if a customer is looking to take the material, take the pastilles or the pitch and sell it to the open market space, then typically to produce less, thus a pastillation scheme would be advisable. Whereas the flake process, typically the customers who actually have flake processes, they typically use the flake within the refinery gates in a CFB application. So the dust is not such a big issue, or I should say the fines are not such a big issue. There are roughly 4 or 5 plants globally producing asphaltene pitch based on steel belt technology. I'd like to go in and show the group a reference plant that IPCO supplied a few years ago to a customer in China who was operating a COTC, a crude oil to chemical plant. Within this reference case, we worked with one of the global licensors. They supplied their ebulated bed reactor. From the EB bed reactor, the vacuum residue stream was fed to their solvent deasphalting unit. And from the SDA unit, basically IPCO received the pitch stream into our battery limit. Within IPCO's battery limit, we supplied our flaking technology to produce basically flake pitch, which was conveyed and sent to an on-site gasifier. As I stated previously, the project highlights included the EB bed reactor, SDA unit, pitch solidification, and the customer supplied the gasification unit. IPCO's scope supply included 12 plus 2 cooling units, 12 operational, and 2 standby units. The scope supply also included the liquid pitch feeding system, the cooling water system, the exhaust system, the pitch product breaker, and the solid pitch conveying system. What we're seeing here is the pitch feeding system. IPCO supplied a heated weir box with a jacketed dual feed manifold and also a overflow control gate to control the thickness of the liquid layer, and an exhaust hood to exhaust the fumes. And run the video. As you can see, the pitch is being fed from the manifold into the heated weir box. And here is the overflow gate, so we control the layer thickness that we will cast on the actual steel belt. In this next slide, you're seeing a overflow plate, a heated overflow plate that took the liquid pitch to a specific thickness and cast it onto a steel belt. In this next slide, as you can see, the pitch, this is the inside of the hoods on the steel belt flaker. The pitch is being transferred and cooled and entering the actual product breaker itself for this particular installation. From the product breaker, the random size particles were broken and fed to a takeaway conveyor. And the takeaway conveyor conveyed the broken pitch random flake to the pitch storage system. I would like to conclude my presentation by making a compelling case as to why customers or clients should consider pitch solidification in combination with the SDA unit. We believe that this combination of technologies should be considered for the various residue upgrading schemes. Pitch solidification in combination with an SDA unit, we believe, is an attractive alternative to coking, especially for a greenfield plant where a coker does not exist. First, primarily, the liquid yields and revenue generation will be higher based on the SDA unit as compared to coking. When we take a look at these examples, most of our clients immediately understand that there are significant CapEx advantages when you compare a SDA plus pitch solidification versus the CapEx cost of delayed coker. Thus, the ROI payback is much faster as compared to coking. Another key soft advantage is when you take a look at refiners who do not have an infrastructure to manage or trade coke. Pitch solidification plus solvent deasphalting is an excellent choice, as the pitch is typically consumed within the refinery gates in a CFB for these customers. And another important softer factor is when you take a look at the unit availability, or the on-stream factor is definitely more favorable for pitch solidification, as pitch solidification could run continuously and does not require cleaning of coking drums. I thank you very much for your time. IPCO is very delighted to be here to present our solutions to the industry. Thank you.